Welcome to today's deep dive. So our mission today is to take this highly technical, incredibly dense engineering rulebook and, well, translate it. We want to really explore how these giant industrial mega projects, power plants, refineries, how they're actually safely brought to life.
Right, because it's not magic. It's obsessive rule following.
Exactly.
Yeah.
And the source document we have on the table for this is the scope of work for testing pipe systems. This is specifically the pre-commissioning and system testing sections under the FIDC Conditions of Contract for Construction, which is the second edition from 2017.
Better known in the industry as the Red Book.
Yeah, the Red Book. And I mean, if you've ever driven past one of those massive industrial complexes and just looked at the hundreds of miles of steel piping, you've probably wondered, like, why don't these things just burst? You've got explosive gases, high-pressure steam all pumping through them. Or, how does a billion-dollar turbine survive its very first day on the job without just being completely destroyed by some random piece of construction dust?
It's a great question. And the answer really lies in these obsessive, rigorous testing rules that we're unpacking today. I want you to just sort of picture the scene here. Imagine the backdrop changing to a sprawling industrial construction site. You've got complex blueprints everywhere, massive steel pipelines, scaffolding.
Organized chaos, basically.
Exactly, yeah. And my role today is to explain not just what these tests are, but why the extreme, almost punishing rigidity of this FEA Red Book framework is literally the only thing standing between a successful mega project and a complete catastrophic failure.
So, to start, before you can even put a single pipe under pressure, you kind of have to understand the rules of the game, right? And importantly, who holds the power.
Oh, absolutely. The contract dynamics are everything. The FADA Red Book sets up this very clear dynamic between the contractor and the engineer.
Right.
The contractor is the one actually doing the physical work, and they are the ones paying for the failures. But the engineer, acting as the employer's representative under subclause 3.1, they hold all the approval power.
And they don't mess around with the schedule either. I mean, looking at the submittal schedule, the contractor has to submit a master testing program, a full 28 days in advance?
Yes, 28 days for the master plan. And then for individual test procedures, those have to be submitted 21 days in advance.
Wow.
Yeah, because the engineer needs that lead time. They have to review pressure calculations, safety exclusion zones, all of it.
So you can't just, weld a pipe and test it the next morning.
Not even close. And that brings us to the inspection regime, which is heavily reliant on two things: hold points and witness points.
Okay, let's unpack this because I was thinking about how to explain this.
Yeah.
A hold point is kind of like a TSA security checkpoint at the airport, right? You absolutely cannot proceed until they physically clear you.
That's a perfect analogy, actually.
Yeah. And then a witness point is more like your flight's boarding call. They notify you it's happening, but, if you don't show up at the gate, the plane is leaving without you. The test proceeds whether the engineer is there or not.
Exactly. If the contractor gives the proper notice for a witness point and the engineer doesn't show, the contractor can just run the test and submit the results. But if they skip a hold point, all work stops. And the financial stakes here, which are defined in subclauses 9.3 and 9.4, are just staggering.
Right, because who pays if a test fails?
The contractor. Always. They bear the cost of retesting, the labor, the equipment. And if those failed tests cause delays, they face performance damages, which are outlined in Annex B.
Liquidated damages, which on a billion-dollar project
Can be financially ruinous. We were talking massive daily penalties. And ultimately, they can't get the taking over certificate under subclause 10.1 until everything passes. No certificate means the project isn't officially handed over. No final payments.
which is just a crazy amount of pressure. But speaking of pressure, let's get into the actual physical testing. We've got the rules, we know the referees.
Right.
Now we have to actually stress test these pipes to prove they are mechanically sound before any dangerous fluids are introduced.
Yes. And the baseline for this is hydrostatic testing.
Which is water,
Yeah.
right?
Correct. Clean, potable water. The contractor seals the system and pressurizes it to 1.5 times the design pressure, so they are intentionally pushing the steel way beyond its normal operating limit.
A 50% safety margin, that's huge.
It is, and they hold it there for at least 30 minutes. The acceptance criteria during that half hour are brutal. 0 visible leakage. The pressure loss cannot exceed 0.1 bar.
0.1 bar, that's basically nothing.
Right, it's a microscopic margin of error, and there can be 0 permanent deformation of the steel.
But then I noticed there's this weird rule where they have to drain and dry it really fast, right? Within 48 hours?
Yes, within 48 hours, because if you leave heavily oxygenated water sitting in raw carbon steel, you're going to get immediate flash rusting, which ruins the pipe you just proved was sound.
Makes sense. But here's where it gets really interesting to me. Hydrostatic uses water, but sometimes they use pneumatic testing, which is gas. Why would anyone use air instead of water? I mean, if a water pipe bursts under pressure, it's like a water balloon popping. It's messy, sure, but it's manageable. But a pipe bursting under compressed gas is literally like a bomb going off due to the stored energy.
It absolutely is. The physics are entirely different. Gases compress, liquids generally don't. So compressing air or nitrogen stores massive kinetic energy. If a weld fails during a pneumatic test, the steel basically becomes shrapnel.
Wow. So why do they even do it?
Well, because they have to. Some systems absolutely cannot get wet. Ever. Think about instrument air systems that run sensitive valves, or dry gas lines, or cryogenic systems operating at hundreds of degrees below zero.
Oh, because if there's even a drop of water left behind in a cryogenic pipe.
Exactly. It freezes, expands, and destroys the internal seals the second the plant turns on. So for those systems, you have to use pneumatic testing. But because it's a quote-unquote safety-critical activity, the rules will change. You only pressurize to 1.1 times the design pressure, not 1.5.
Okay, so a much lower threshold.
Right, and you stage it. 10%, then 50%, then full pressure. You use a soap solution to check for bubbling leaks. But the safety protocols are intense. Strict exclusion zones. Pressure relief valves physically set at 110% to prevent accidental overpressurization.
And nobody's allowed to, like, weld nearby.
Total ban. Absolute ban on welding, cutting, or grinding anywhere near this system.
Sounds terrifying,
Yeah.
honestly. But okay, so now we know the pipes won't burst. But we face a totally new problem. Construction is inherently dirty. I mean, these pipes are sitting out in the dust, guys are welding them. They're filled with welding slag, rust, sand.
Yes.
And we have to surgically clean the insides, which brings us to the internal car wash phase.
That's a good way to put it. The first step is usually water flushing, pumping water through at a minimum of 1.5 meters per second to literally blast out the loose debris.
And they actually measure how clear the water is when it comes out, right?
Yeah, they do. The turbidity, the cloudiness cannot exceed 10 NTU, so it basically has to look clear. But water only gets the loose stuff. For the heavy hydrocarbons, grease, and baked-on rust, you need chemical cleaning.
And this is hardcore. I was reading this part. It's a full 6-stage process.
It's chemistry on an industrial scale. Stage 1 is degreasing to break down the oils. Stage 2 is pickling, where they use a strong acid to literally eat away the rust and mill scale down to the bare metal.
Which sounds like it would just destroy the pipe if you left it in
There would, which is why Stage 3 is neutralization to balance the pH. Followed by Stage 4, a massive rinse targeting a neutral pH of 6.5 to 7.5.
Okay, so now you have perfectly clean, bare steel.
Right, but bare steel flash rusts instantly if oxygen hits it.
So that's stage 5, passivation.
Exactly. They circulate a chemical that creates a microscopic protective oxide film over the steel. It's essentially controlled rusting to prevent uncontrolled rusting. And then Stage 6 is drying.
But even with all that acid washing, for the really high-end stuff like high-pressure steam turbines, they have to go a step further. Steam blowing.
Yes, steam blowing is the ultimate test of cleanliness.
I am kind of obsessed with the acceptance criteria for this. So they shoot high-velocity steam through the pipes and aim it at a target plate, which is this polished stainless steel plate, exactly 150 millimeters by 150 millimeters.
A literal mirror.
Right. So what does this mean? They're essentially shooting a hot sand blaster at a mirror, and the test fails if there is a single dent larger than 0.8 millimeters. That is just wild precision.
It is. But when you look at the big picture, you understand why. Why such microscopic precision? Because a modern steam turbine has blades spinning at thousands of RPMs. If a tiny piece of metal debris, even a millimeter wide, bypasses that pipe and hits a blade,
It just shreds the turbine.
instantly.
Wow.
It acts like a bullet. It fractures one blade, which shears off, hits the next row, and within seconds, your billion-dollar turbine is scrap metal.
Unbelievable.
Oh.
And doing this kind of cleaning must be an environmental nightmare.
It's heavily regulated. For chemical cleaning, the contractor has to have a chemical waste management plan to safely dispose of thousands of gallons of neutralized acid. And for steam blowing, you're venting high-pressure steam to the atmosphere. It's deafening. They require noise assessments and mandated hearing protection for anyone within 50 meters.
Wow. Okay, so we've got the pipes strong, they're surgically clean, but the plant might not open for months. If you just leave them sitting there, oxygen and moisture are going to get in and ruin all that hard work.
Which brings us to the final hurdle, drying and preservation.
Bone dry and bottled up.
Exactly. For drying, they use air, hot air, vacuum systems, or nitrogen. And the acceptance criteria here is brutal. They have to continuously monitor the air coming out of the pipe until the system hits a dew point of minus 40 degrees Celsius.
Why not 40? That's freezing.
And it has to hold that minus 40 reading for 30 uninterrupted minutes. Only then is it considered completely devoid of moisture.
Okay, and then to keep it that way, they use preservation. I saw things like desiccant breeders with color change indicators, chemical corrosion inhibitors, but the big one seems to be nitrogen blanketing. They pump it full of nitrogen and maintain a positive pressure of zero point 0.1 to zero point 0.3 bar G.
Correct. Nitrogen is inert, so it displaces the oxygen.
It's so funny. When I read that, I realized it's exactly like how potato chip companies fill the bags with nitrogen so the chips don't get stale or crushed.
Yeah, that's the exact same thermodynamic principle.
Except here, we're doing it to miles of industrial steel piping to stave off microbial growth and rust.
Exactly. And once that nitrogen blanket is sealed in, it completes the final stage. It seals what they call the test dossier, completing this massive 9-step pre-commissioning sequence, everything from mechanical completion all the way to system handover.
And that perfectly preserved state is what lets the contractor finally knock on the engineer's door and say, hey, we're ready for the tests on completion under subclause 9.1. Man, what a journey. So we've basically taken a pile of dirty, rusty steel pipes and put them through the absolute ringer. We've hydro-tested them to 150% capacity, acid-washed them, steam-blasted them until they are perfectly smooth, dried them to a freezing minus 40-degree dew point, and finally sealed them in a giant bag of nitrogen.
It is a staggering amount of engineering.
It really is. So the next time you drive past a massive power plant or an oil refinery, you really should think about this invisible, obsessive 9-step regimen, because that is the only thing keeping that facility from blowing sky high.
It really is. And, I want to leave you with one final thought to ponder that really builds on all this text. We talked about the taking over certificate under subclause 10.1. That is the exact moment the employer actually takes ownership of this multi-billion-dollar facility.
Right at the finish line.
But that certificate cannot be issued until every single one of these tests is passed and countersigned by the engineer. So just imagine the immense psychological tension and the sheer financial pressure on the exact day of that final steam blow or that final hydro test.
Oh man, the stress in that room.
Exactly. What happens in the control room when a multi-billion-dollar handover is delayed by a single 0.9 millimeter scratch on a metal target plate or a 0.15 bar pressure drop on a gauge?
Somebody's definitely losing their job.
Or millions of dollars in liquidated damages are triggered. The engineering we discussed today is a perfect, rigid science. But the human drama behind those test record sheets, the arguments over fractions of a millimeter, it must be staggering.
That is such a fascinating point, the intersection of microscopic tolerances and massive financial panic. Well, that is all for our deep dive today. Thank you so much for joining us as we explored the hidden world of industrial pre-commissioning. Keep questioning the systems operating around you, and we will see you on the next one.
See the link in the description for free PDF download. Also, watch our other construction scope videos. Thanks for watching. Please subscribe and see you next time.